So the last class we have seen various symmetry operations and what are symmetry elements and the symmetry operations we could explain yesterday. And today I'm going to explain the same concept with some of the models which I have made. And the first model I would like to take is the water molecule. Actually, I have asked you to prepare your own models at home so that you can easily understand, but I don't know how many of you have done. Just I have taken, are you able to see this? This is the water molecule. So this is oxygen, and here is a hydrogen, and here is a hydrogen. This is the water molecule. With the water molecule, we can start. You can assume a rotational axis, an axis of rotation here. I will show you the axis of rotation. Look here. Suppose if this is the axis, you can rotate the molecule about this axis. When you rotate the molecule about this axis for an angle of 180 degree, it rotates and it becomes like this. Now the hydrogen that was here is rotated and it comes over here, and the hydrogen here, it comes over there. Therefore, in one full rotation, it assumes 2 times the identical configurations. Therefore, this axis is called a C2 axis. Similarly, this molecule can be cut into 2 equal halves. You can assume a plane here. Suppose if you are assuming a plane which cuts the molecule into 2, and this plane is a reflection plane, which is a mirror which can reflect on both sides, then what will happen? This hydrogen will be reflected over here, and this hydrogen will be reflected over here. Therefore, this has the plane of symmetry. This is the plane. Now, this is a plane of symmetry. The water molecule contains one more plane, which is the molecular plane, a plane which cuts the molecule into 2 thin sheet-like structures. And the front part can be reflected over the back part, and the back part can be reflected over the front part. Therefore, it contains one more reflection plane. And I want to tell you one thing. I have already told you the idea of principal axis. Principal axis means if many axes are present in a molecule, that axis with the maximum number of order. Suppose if a molecule has a C3 axis and a C2 axis, then C3 axis is the principal axis. Suppose if a molecule has more than one axis with the same order, then that axis which passes through maximum number of atoms will be the principal axis. Now look here, the water molecule contains only one axis, which is the C2 axis. Therefore, that is the principal axis. Now, the reflection plane, this is the plane. The plane is containing the principal axis. The principal axis is present in the plane. Therefore, the plane which contains the principal axis is called vertical plane sigma v. So this idea you should always remember. The plane which contains the principal axis is called vertical plane sigma v. And you can assume one more plane here, that is, I have already told you, the molecular plane. The molecular plane itself is a plane of a symmetry, and that plane also containing the principal axis. Therefore, water molecule contains 2 vertical planes, and this is a vertical plane, and this is also a vertical plane. So in order to differentiate the vertical planes, this is called sigma v, sigma suffix v, and this plane is called sigma v dash. Now I'm going to explain the same symmetry elements and symmetry operations with one more model. Let us assume that this is ammonia model. Just I have taken an old sketch and I cut and I made this ammonia molecule. Look at this ammonia molecule. Look at this ammonia molecule. Anybody is in the waiting room? Somebody has raised their hand. Pavitra. Pavitra, what is your doubt?
Sir, apply தெரியாம அமைக்கிட்டேன்னு சொன்னாங்களா சார்?
Okay. It is still raised. Their hands are still raised. Okay. Have you have you all sent your register number and name? Please, all of you send your register number and name in the chat box. So totally 22 are present, and many of you have not turned up. And this is a very important class. Please try to attend without absenting yourself, because if you are not regular, you cannot understand anything in group theory. So now this is ammonia molecule. Look at this ammonia molecule. So ammonia, what is the difference between ammonia molecule and the boron trifluoride molecule? The last class itself I was explaining, but I don't know how many of you could remember that. So this is the model of a boron trifluoride molecule. So boron is at the center. Here is a fluorine atom, and here is a fluorine atom, and here is a fluorine atom. This is triangular planar. The molecule is a planar. See, all the BF bonds are coplanar. They are all existing in one plane. But this is BF3, this is NH3. But ammonia molecule, it is not a planar. It is in the pyramidal shape. It's in the pyramidal shape. Actually, this pyramidal shape is because of the lone pair that is present on the nitrogen. So because of the lone pair bond pair interaction, the bonds are bent. That is why it is assuming the pyramidal shape. Normally, before learning group theory, you're supposed to learn the valence shell electron pair repulsion theory. So because of this electron repulsion, the bond pair lone pair interaction, ammonia molecule, the bonds are bent and it assumes a pyramidal shape. Now look here. So this is boron trifluoride molecule, where you can assume an axis here. This is an axis. This is an axis of symmetry. Look at this axis. This is an axis passing through the boron. Now I rotate the molecule for an angle of 120 degree. I am getting an equivalent configuration. And I rotate the molecule for one more 120 degree. I am getting an equivalent configuration. When I rotate it for one more 120 degree, I am getting the same configuration. Therefore, in one full rotation, the molecule assumes 3 identical configurations. And also the minimum rotation that has to be done to get the first identical configuration is 120 degree. Therefore, 360 divided by 120, 360 divided by 120, you are getting 3. So the axis is C3 axis. This is the C3 axis. Now you can assume an axis here also. This is also an axis. This is also an axis. You can rotate, as in the case of water molecule, you can rotate the molecule like this. So this is a C2 axis. Similarly, along this bond, you can assume one more axis, which is a C2 axis. Along this bond, you can assume one more axis. This is also C2 axis. Therefore, the boron trifluoride molecule contains one C3 axis and 3 C2 axis. So you should thoroughly understand the boron trifluoride molecule contains one C3 axis and 3 C2 axis. Now, you can assume a plane here. You can assume a plane here. The plane, as in the case of water molecule, which cuts the molecule into 2. And here also one more plane you can assume, which cuts the molecule into 2 halves. When they are reflected one over the other, you are getting an identical configuration. And here also you are assuming a plane which can cut the molecule into 2, where one can be reflected over the other. And also, as it was in the water molecule, you can assume a plane which cuts the molecule into 2 thin half sheets. That is the molecular plane itself. Now my question is, I have already told you the boron trifluoride molecule contains one C3 axis and 3 C2 axis. Which is the principal axis of the molecule? The principal axis is that axis with the maximum number of order. Therefore, the C3 axis is the principal axis. So the C3 axis is the principal axis means, look, watch carefully. If the C3 axis is the principal axis means, the plane which cuts the molecule into two along one BF bond, this is the principal axis. The plane which cuts the molecule into two like this, now the plane is containing the principal axis, therefore this is a vertical plane, sigma v. Similarly, here is a plane. Now the plane contains the principal axis, which is a vertical plane. Now this is another plane which cuts the molecule into two, and this plane is also a vertical plane. Now you can assume this plane, the plane which cuts the molecule into two thin half sheets like structures, this plane is perpendicular to the principal axis. Are you able to understand? This plane, the plane which cuts, that is the molecular plane is perpendicular to the principal axis. Therefore, that plane is called horizontal plane, sigma h, sigma suffix h. See, therefore, if you take the BF3 molecule, it contains one C3 axis, this is the C3 axis, and 2 and 3 C2 axis. One axis is along here, and one axis is along here, and another axis is passing through this BF bond. Therefore, it contains 3 C2 axis, and 3 C2 axis contain 3 sigma V's also. This is one sigma V, and this is another sigma V, and this is another sigma V, and it also contains one sigma H, that is the molecular plane. So these are all the symmetry elements present in the boron trifluoride molecule. But if you look at the ammonia molecule, you can assume a C3 axis here. This is a C3 axis. So if the molecule is rotated about this C3 axis, this hydrogen goes over there when you rotate the molecule by an angle of 120 degree, and this hydrogen goes over there when you rotate the molecule for an angle of 120 degree. Therefore, 3 times it assumes the identical configuration in one full rotation, or I can calculate like this also. The minimum rotation to be made to get the first equivalent configuration is 120 degree. Therefore, 360 divided by 120, you are getting C3 axis. So this is C3 axis. So C3 axis is present here. But you cannot assume any C2 axis in the case of ammonia molecule, as in the case of boron trifluoride molecule. Boron trifluoride molecule contains a C2 axis. But ammonia, it is not containing C2 axis. Because if you assume any axis along the NH bond, and if you rotate for 180 degree, you will be getting just an inverted configuration. It goes up and down. You are not getting equivalent configuration. If you rotate the molecule like this, what will happen? You are not getting equivalent configuration. Therefore, ammonia molecule does not contain C2 axis. But ammonia molecule contains sigma V, a plane which can cut the molecule along an NH bond, and a plane which cuts the molecule along the NH bond, and the plane which cuts the molecule along the NH bond. All these 3 planes are the principal, they are all containing the principal axis. It has only one axis, which is the C3 axis, and which contains all the planes are containing the principal axis. Therefore, I can say ammonia molecule contains one C3 axis and 3 vertical planes. Therefore, the 3 vertical planes are denoted as sigma V dash, sigma V double dash, and sigma V triple dash. This is how the 3 vertical planes are mentioned. Therefore, the water molecule contains identity element E. Identity element is doing nothing. All the molecules are containing identity element. So identity element E, and then a C2 axis, and then 2 reflection planes. And these 2 reflection planes are vertical planes. Why they are vertical planes? Because they contain the principal axis. And one vertical plane is in between here. Another vertical plane is the molecular plane. Therefore, what are all the symmetry elements present in water molecule? E, C2, sigma V, and sigma V dash. So these are the symmetry elements present in the water molecule. Where are these elements present? The C2 is here, sigma V, one sigma V is here, another sigma V is here. Therefore, these are all the positions of various symmetry elements in the water molecule. If you take a boron trifluoride molecule, it contains E, identity element is present in all the molecules, E. It contains a C3 here, C3 axis here. It contains a C2 axis here, C2 axis here, and C2 axis here, and a sigma V here, a sigma V here, a sigma V here, and a sigma H, that is the molecular plane. Therefore, boron trifluoride contains identity element, C3 axis, 3 C2 axis, and 3 vertical planes, and 1 horizontal plane. So these are all the symmetry elements present in the BF3 molecule. If you take the ammonia molecule contains E and 1 C3 axis which passes through the nitrogen, and 3 vertical planes which bisect the molecule along each NH bond. Therefore, it contains E, C3, sigma V dash, sigma V double dash, and sigma V double dash. So these many water molecules are, these many symmetry elements are present in the ammonia molecule. Next one, I have already told you in the last class, there is one more axis called the improper axis of symmetry. This improper axis of symmetry, you have to understand with a little more attention. Look at this molecule. Actually, I wanted every student to make your own models so that you can understand well. So this is ethane. This is ethane. So a carbon connected through a single bond is a CH bond, CH, and a CH bond, CH. So this is ethane. Just I have taken a pin and I cut the refill and I have connected and I'm getting an ethane molecule. This is ethane. If you look at the ethane like this, look here. If one CH bond exactly overlaps on the other CH bond, this configuration is called eclipsed configuration. Eclipsed. This is called eclipsed. This you might have studied in the first year organic chemistry. Conformational isomers. The conformational isomerism is arising due to the rotation of carbon-carbon single bond. This is called eclipsed configuration. Suppose if the bonds are little bit turned and see the front carbon, the CH bond is falling exactly in between the CH bonds of the rear carbon. Look here. Now this configuration is called staggered configuration. Staggered. So if they are perfectly aligned one over the other, it is called eclipsed configuration. See, look here. One carbohydrogen and another carbohydrogen, they fall on one over the other. Eclipsed configuration. If they come in between, it's called staggered configuration. Staggered. Look here. Staggered configuration. Now, when it is the eclipsed configuration, this is the eclipsed configuration. I suppose you are all able to see. This is the eclipsed configuration. If you take the eclipsed configuration, You can assume an axis passing through CC bond. If you assume an axis passing through CC bond, when you turn the molecule for an angle of 120 degree, you are getting identical configuration. When you are rotating the molecule for another 120 degree, you are getting identical configuration. When you rotate the molecule for another 120 degree, you are getting identical configuration. Therefore, in one full rotation, it assumes 3 times the equivalent configuration. Therefore, this is a C3 axis. This is a C3 axis. So the C3 axis is passing through the CC bond. And also it has a reflection plane. You can assume a plane over here. This is a plane. This is a plane. A plane which passes through the CH bond. And here is a plane which passes through the CH bond. And here is a plane which passes through the CH bond. Therefore, as it was discussed in the case of ammonia, the eclipsed configuration, it contains 3 sigma V's. It contains sigma V's. And you can assume one more plane here which cuts the molecule like this. And this plane is perpendicular to the principal axis. Therefore, this is sigma H. This sigma H. Now, this axis is called the proper axis of symmetry because you are getting the equivalent configuration simply by rotation. Nothing else you have done. You rotate the molecule and you are getting the equivalent configuration. This is a proper axis. Suppose if I take the staggered configuration, look here, watch closely. I don't know how much it is visible to you. Watch closely. This is the staggered configuration. I suppose you understand now. This is a staggered configuration. If you rotate the molecule for an angle of 120 degree, you are getting identical configuration, no doubt about it. When you rotate the molecule for an angle of 120 degree, you are getting an identical configuration, no doubt about it. But when you rotate the molecule for an angle of 60 degree, what happens? Watch closely. Watch closely. I am rotating the molecule for an angle of 60 degree. What happens? This is not an identical configuration. This is not an identical configuration. So, look here. Now, I think the projection now, the carbon which is on my side has a CH bond projecting upward. Is that right? The carbon which is on the viewer's side, that is your side, the CH bond is projecting downward. Let us have this as an identity. Now I rotate the molecule for an angle of 60 degree. 60 degree. What happens now? The CH bond which projects towards the viewer is now up. The CH bond which is here, which is towards me, is down. Therefore, this is not equivalent configuration. I can get an equivalent configuration when I am able to reflect, when I am able to reflect this portion over there and that portion over here. When I am assuming a reflection plane which is perpendicular to the axis of rotation, I am rotating about this axis, I turn, which is followed by a reflection about a plane which is perpendicular to the principal axis. Now I am getting an equivalent configuration. This is called improper axis of symmetry. A rotation followed by a reflection in a perpendicular plane. A rotation followed by reflection in a perpendicular plane is called improper axis of symmetry, which has the symbol SN. Yes, N is the order. So here the minimum angle to be rotated to get an improper axis is 60 degree. Therefore, the staggered ethane molecule contains S6 axis. S6. So C3 axis also present. S6 axis is present. S6 is equal to C6 sigma. C6 sigma is S6. S6 axis is C6 sigma. Therefore, the staggered ethane molecule is containing S6 axis, that is improper axis of symmetry. If you are not able to understand improper axis of symmetry, I have made one more model to explain that clearly. I don't know. So this is simply I made of a small wire to explain the allene system. Allene, the speciality of allene is, look here, allene molecule is a CH2, C double bond, C double bond, C H2. This is an allene. And actually, the three-dimensional structure of allene is these two hydrogens are horizontal. Then the double bond is vertical. Then this double bond is horizontal, and these hydrogens are vertical. So vertical, horizontal, vertical, horizontal. This is how allene structure is present. Look here, I can rotate, then you can see the molecule. I can rotate. Now see. Now, so these two hydrogens are vertical, these two hydrogens are horizontal. I am assuming an axis here, and I rotate the molecule for an angle of 180 degree. I am getting equivalent configuration. Again, on my left it is vertical, on my right it is horizontal. Is that right? So this contains a C2 axis which is passing through the CC bonds. Suppose I rotate for an angle of 90 degree, what will happen? When I rotate for an angle of 90 degree, on my left it becomes horizontal, on my right it becomes vertical, which is not the original configuration. See, this is the original configuration. I want to get a configuration which is equivalent to this. I should get any configuration where the two hydrogens on my left should be vertical and the two hydrogens on my right should be horizontal. So when I rotate the molecule for an angle of 180 degree, I am getting with a configuration with two hydrogens vertical on my left, two hydrogens horizontal on my right. But when I rotate the molecule for an angle of 90 degree, on my left it becomes a horizontal, on my right it becomes vertical. This is not the identical configuration. How to make it identical? You can reflect about this plane, that is the plane which is perpendicular to the axis of rotation where you rotated. When you reflect about this plane, what will happen? Automatically this portion will be reflected over here and this portion will be reflected over there. You will get like this. Just for your sake I have turned. Actually it is reflection. Now what happens? On my left I am getting vertical hydrogens, on my right I am getting horizontal hydrogens. This is the equivalent configuration. Therefore, a rotation followed by a reflection about a perpendicular plane. Now this axis is called S4 axis. This axis is C2 axis and also it is S4 axis, because for C2 axis we are rotating for 180 degree and we are getting identical configuration, and for S4 axis we are rotating for an angle of 90 degree and we are getting equivalent configuration. So when we rotate it for 90 degree and reflect about a plane which is perpendicular to the axis of rotation, I am getting equivalent configuration. This is called improper axis of symmetry. So improper axis and proper axis of symmetry, what is the difference? When you get an equivalent configuration simply by rotation, it is a proper axis of symmetry. When you rotate the molecule, which is followed by reflection about a plane which is perpendicular to the axis of rotation, if you get equivalent configuration, it is called improper axis of symmetry. The improper axis of symmetry will be given the symbol S. So this has S4 axis, S4 axis. So this is about the improper axis of symmetry. Now I'm going to show you the tetrahedral shape. This is tetrahedral shape. It's a methane molecule in a tetrahedral shape. You can assume C3 axis along every bond. This is C3 axis. This is C3 axis. This is C3 axis. C3 axis along every bond, tetrahedral structure, and the C2 axis along the in-between point between two bonds of the hydrogen and the carbon. If you assume an axis here, you can see the C2 axis. If you are not able to visualize this, try to construct your own model. Try to construct your own model and then try to identify various symmetry elements present in the molecule. Then you can easily understand. Now look, one more structure I would like to show you. My dear students, we have not yet given your attendance in the form of chat. Just type your register number and the name in the chat box. Write your register number and the name in the chat box so that I can see how many of you are present. Those who have come late, please type your register number and the name in the chat box. Right. So I have shown you so many structures today. So this is a model for ethylene structure. Ethylene structure, this is CC double bond. This is CH hydrogen, this is CH, this is CH, this is CH. So ethylene has C2 axis. When you rotate the molecule for an angle of 180 degree, you are getting identical configuration. The C2 axis can also be assumed here. You can rotate the molecule like this also. Here also one C2 axis. You can rotate the molecule like this also. Here is also one C2 axis. Now you see, here is one C2 axis, here is one C2 axis, and here is one C2 axis. If a 3 C2 axes are present, that axis which passes through maximum number of atoms. See, this axis is passing through 2 carbon atoms. So that axis which passes through maximum number of atoms is the principal axis. Therefore, now you can cut the molecule. You can reflect the molecule about this plane. So this is the principal axis. So this plane is containing the principal axis. Therefore, this is vertical plane. Even this molecular plane is also containing the principal axis. Therefore, it is also a vertical plane. Suppose if you assume a plane here, the plane which reflects the left part over right and right part over left, this is also a reflection plane, but this plane is perpendicular to the principal axis. Therefore, this is horizontal plane. Therefore, that plane which contains the principal axis is vertical plane, which is denoted as a sigma v. And that plane which is perpendicular to the principal axis is a horizontal plane, which is sigma h. And there is one more plane which is called dihedral plane. Dihedral mean, look here, dihedral planes are found in alene systems. Diagonally, you can assume a C2 axis. Diagonally, you can assume a C2 axis. Even in this fashion, you can assume a C2 axis. Therefore, the C2 axes are intersecting each other in the case of allenes. The C2 axes are intersecting each other. You can assume a plane which bisects these two intersecting C2 axes along the point where the axes intersect. That plane is called dihedral plane sigma d. Actually, after we come to the college, I will show you the model. We have a model for dihedral plane. Dihedral plane will bisect two C2 axes which are intersecting. Just you take down this thing and you can go to any literature and you can see. Dihedral plane is a plane which bisects two intersecting C2 axes. So which is present in alene. This is alene structure. And that's all. I think I have shown you all the models. So this is staggered ethane model. I think you have understood everything. This is ammonia model, staggered ethane model, and this is boron trifluoride model, and this is water molecule. Therefore, first of all, what you should do, you should draw the molecular structure of various molecules, and then still somebody is in the waiting room. I want everybody to come on time because almost the class is going to be over. Therefore, I request all of you to attend the class on time. If you miss one class, you cannot understand anything. So now look here. First, you write the structures of simple molecules like methane, methyl chloride. You can take down all these things: methane, methyl chloride, dichloromethane, ammonia, boron trifluoride, hydrogen peroxide, benzene, chlorobenzene, trichlorobenzene. You can write all these molecular structures and try to understand what are all the symmetry elements present in these molecules. And then you have to find out what happens when operations are carried out using these symmetry elements. So when you do the operations, how you are getting the identical configuration, you have to do by yourself, and you have to draw the structures by yourself, and you have to understand. So the symmetry operations present in a molecule, when they are put together, they form a group. This is where actually the mathematical group theory comes into the picture. The symmetry operations present in a molecule, when they are put together, they form a group. What is a group? Mathematical group. If a set of elements, they satisfy 4 important conditions, then they are set to form a group. The first condition is the closure rule. Closure rule means any 2 elements of the group should combine to result in an element which should also be a member of the group. So that is the closure rule. Second one, the operation should be associative. That is, A star B star C should be equal to A star B star C. In the next class, I will put everything in the PowerPoint mode so that you can understand. And the third property is the presence of identity element in the group. There should be one element in the group which should commute with all the elements. It should have identity element. And the fourth one is every element of the group should have its own inverse element in the same group. If these 4 conditions are satisfied, then the elements in a set, they form a group. Now the symmetry operations in a molecule, when they are put together in a set, they form a group. And if all the elements commute with each other, then it is called an abelian group. If all the elements of the group are generated from one element of the group, then it is called a cyclic group. All cyclic groups are abelian groups, but all abelian groups are not cyclic groups. Similarly, all abelian groups are groups, but all groups are not abelian groups. Therefore, there are 4 important characteristics. First, the group should obey the closure rule. Second, it should have identity element. Third, it should have its own inverse element in the group. And the fourth one, the function should be associative. And apart from this 4, if all the elements commute, it is abelian group. And the sixth one, If all the elements could be generated from one element of the group, then it is a cyclic group. So the next class, what I will do, I will be working out all the symmetry operations present in a few molecules, and then I will prove how these operations form a group. In order to prove that the operations in a molecule form a group, we are going to construct a table called multiplication table. When you construct the multiplication table, very easily you can prove that the important properties of a group are possessed by the group containing the symmetry operations in the molecule. So with that, we come to the end of this class, and those who have not yet given their attendance in the chat box, so please do it fast. And I thank you very much for this meeting. And before the next meeting, I will give you the invitation through Google Class. And I request all of you to enroll yourself in the Google Classroom that is allotted for you. That is Physical Chemistry 1 and Physical Chemistry 2 for third year BSc Chemistry 2020-21 batch. You please do not look into the old Google Classroom thermodynamics. I'm not going to use that. And these two things are there. Whenever Physical Chemistry 1 class is there, you will get the intimation through the Physical Chemistry 1 Google Classroom. And whenever Physical Chemistry 2 class is there, you will get the invitation in the Physical Chemistry 2 classroom. Therefore, today I have seen only 20 or 21 have been registered, Therefore, I request all of you to register today itself and also be on time for the class. If you miss the class, you will not be able to understand anything. Therefore, I request all of you, I think 29 have come. So, thank you very much, and let us meet in the next class.
Sir, நிறைய பேருக்கு நெட் முடிஞ்சிட்டேன்னு வரல.
Okay, ma. Thank you very much.